should have done more questions, because I looked at what the old version of it was, and honestly, it was just really a bunch of really tricky questions and how to work your way through it. And that, I think, is probably the best use of time. But anyway, speaking of use of time, I'll go ahead and get going on this. Let me make a co-host, just for anybody who pops in. There we go. So the usual. Okay, so I'll go ahead and let me toss what got taught or submitted. One of the people who submitted questions isn't here yet, so I think their questions are at the end anyway, but handful of questions. So a couple from the fluids chapter, thing on surface tension and pressures, fluid flow, and then some GChem from equilibrium chapter, followed by some acid base, still in the mix. And then these are the ones, if person who submitted gets here, just a series from the first phase, whatever practice test. And so these are they're GChem from all over the map. But I'll go ahead and get started on this then. So starting with fluids, for a question like this, and I mean, personally, I think these questions are some of the most important ones to do, these sort of, how do you explain it in circumstances? And so there's two parts to this question. So before anything happens, we have this contained air region. We have region 1 and region 2, and then you have some membrane here, some phospholipid bilayer. And what happens is somehow, some way, we do something, some reaction occurs, and it distorts. So first off, is it fairly, I'd say, straightforward to say that the wall was pushed to the left? Therefore, it must have experienced an increase in pressure on this side or a decrease in pressure on this other side. And how would agree a drop in pressure this way would allow the wall to move that way, or an increase in pressure? So is the pressure no big deal? I mean, how many are okay with the fact the pressure is distorted? Now, where it gets kind of weird is the concept of surface tension. And I want to just bring something up, and that is, so let me first off get rid of the wrong answer. So we know the pressure in the right side of the vessel has increased. Okay, so surface tension is kind of this weird concept. Do not mistake surface tension for tension. As a general rule, the more you pull on a cable, the greater the tension. Surface tension is kind of the inverse of that. What surface tension says is how tightly that band of molecules is held together, or how tightly molecules are here or here, whatever I'm looking at. But the key thing is, what would you say is true of any sort of membrane? The more you pull on it, are you making molecules closer together or further apart? So when I go from here to here, are the molecules within that membrane now more tightly packed, or are they further apart from one another? Further apart, exactly. Because the total space they're covering is greater. So what surface tension is how hard would I have to pull to rupture that membrane? So as it distorts more and more and more, it's going to be harder or easier to rupture. Easier. So in essence, it has less surface tension. So the perspective I want you to have, the way I want you to define surface tension, the amount of tension you would pull to break apart the surface, if that makes sense. So as it gets stretched more and more and more, you don't have to pull as much to finally break it. So as molecules get further apart, they're held together less tightly, so surface tension actually decreases. So does that make sense then, that surface tension is not a true tension, it's a measure of what force you would have to apply to rupture that? And if you will, because I'm pulling on it, it's a tension force, but it's basically how much you have to stretch it apart. So for instance, why does water have higher surface tension than oil? How can you explain that? It's more tightly packed. There is some truth to that. But what's true of the intermolecular forces between water molecules as opposed to oil? Polar and hydrogen bonding, exactly. So because these polar and hydrogen bonding interactions between water are so strong, what's true of the tension you would need to pull water molecules apart on the surface? If you wanted to go penetrate into that layer, it would be harder or easier to pull them apart. You need a stronger pull to pull water apart, so stronger tension to pull them apart. So water has more surface tension. So it's a weird sort of concept because it's a chemistry term for all intent and purpose thrown into physics, which means the definitions have a little, ambiguity compared to physics. But if it's tightly held, high surface tension. If it's stretched and distorted, if it weakened, it's on the verge of rupturing, it's a low surface tension. So does that make sense then? No. So what would be the vapor pressure? There is some truth to that. So somebody said, I thought when you have higher surface tension, it becomes rounder. So what does that mean? That there is truth to that. So what happens as you get rounder and rounder? Now, this doesn't have the option of becoming round. Now, you're thinking of a droplet. A droplet will become more spherical because it reduces the amount of surface area because it gets more compact. This is actually rupturing. It's not so much getting rounder as much as it's getting distorted and stretched. So if it could go like this, so here's what rounder would be. If this one could turn into this, where it's the exact same length, let's say this is 1 centimeter here and 1 centimeter here, then yes, this would have more surface tension, but it's not necessarily becoming rounder, it's becoming distorted. In order to become round, it would have to break free from there, and turn into a sphere. Does that make sense? This piece would have to come around and touch there. This piece would have to come around and touch there and have to become a droplet. That's what's meant by sphere. So you're taking a concept that you apply to why water beads when you put it on oil or wax or a nonpolar species. And it's totally true. It definitely rounder would be more surface tension because it's reducing its contact point. It's basically aggregating with itself more, so stronger forces. But this one's a little bit different situation. Okay. Next one in this one. This one I really want to go over with everybody because this epitomizes where these two concepts get crossed up. So there's two things. Yeah, Phyllis?
Yes, may I interrupt for a moment? On the previous slide.
Yeah.
So what changes surface tension?
So surface tension, yeah, so if you think about surface tension, it's how tightly do water molecules hold on to each other? So if you think about things that will help have them hold on to each other, number one, stronger forces. So things that have ion interactions, dipole interactions, charge interactions are going to be stronger. So water forms stronger water interactions. So the same things that perhaps make boiling point higher in terms of intermolecular forces also increase surface tension. And then surface tension also has to do with how well they can pack together. So they may have strong forces, but they may not be able to pack together because of structural rigidity or inability to move around and pack together. So that would also weaken it. So anything that allows the molecules to get closer to one another, tighter packed with stronger forces, raises the surface tension.
Okay, thank you.
You're welcome. And then if you think about it, where the term comes from, if you're a diver, is it easier to, if you're a cliff diver, let's say, would it be easier to dive into oil or water? Weird question, but would there be a different? So your goal when you're going in, are you worried about if you hit it too hard, the surface tension will make it seem like a solid? You have to be able to move the water molecules apart in order to go in. So if you notice, what do divers do when they dive in? From high heights? Put their arms in front and make that kind of like V, that triangle shape with their hands. Yeah, so why do they do that? Why do they wedge in like that?
To separate the water molecules or break the surface tension.
Exactly, perfect. They'll wedge their way in and overcome the surface tension. So on oil, pencil dive in my head. I don't know if I've ever done that one, but Oh, yeah, I made that mistake of diving feet first. All our friends jumped off a pier and this is ironic. I totally succumbed to peer pressure while on a pier, but yeah, jumped off the end of it. I didn't realize you're supposed to blow air out of your nose when you go in. Head first would have been so much better. So yeah, that's like one and done. I will never do that one again. So, oh yeah, head
Thank
first
you. I
would be
get it.
horrible.
That was a good
You're welcome.
example.
Anyway, sorry about that. Sorry, I got off my own personal tangent. Sorry. Okay. So for this one, want to address two things. And the biggest thing, the reason I say things the way I say them a lot of times, uh-oh. Can everybody else still hear? Okay, you want to just type,
Yes.
if Monica can't hear, do you want to just rub it in and say you can hear?
No, Monica, it's usually my device.
Yeah. Okay, so. Oh, but can you hear now, hopefully? You hear me talking bad? Oh, she's gone, so, okay. For this, when I say Bernoulli's pressure, did anybody notice I always made a bigger deal pressure against the walls? So does that sound something familiar that always emphasize that? Because this is honestly the biggest confusion that happens in all the fluids of all the years I've taught this. This is the concept that is most confusing to people. So if I consider this tube, let's just ignore everything on the side here for a moment. And if I had a tank of water here, this would be one end. And if this was the other end, then from end to end, I'd worry about the pressure difference because there's a surface here holding it in place. It's going to push back up as much as the water is pushing down, so nothing's going to move. So we don't have to worry about anything. But if I poked a small hole in the bottom, what would happen? Water would flow out because Poiseuille's law, high pressure, low pressure, the weight here would push the water out. But what would happen to the walls? So Poiseuille's would be one end to the other. The walls would then, as a fluid moved and as the height changed, pressure against the walls would change. Here is what's different. Is it flowing down and out here? Is it flowing down and out here, down and out? So is it flowing out through these points? So what we have to consider is the pressure from one end to the other. So let's consider two parts. From here to here, what happens to the pressure as you go down? As you mentioned here, pressure goes up. So pressure goes up as you get lower. Totally true. You nailed that one. Okay. But what's here then, that means it's high pressure here. What is the pressure at the end of this pipe? Yeah, so it's a pressure right at the container at the start of that spigot, start of that exit point. Over here, the exit point is air. And so in this point, you have air, 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 and air. On the other side, you have rho GH, rho GH, rho GH, and rho GH. But as H is going up, it's getting deeper and deeper, the pressure is getting higher. That's why it's pushing from one end to the other, pushing it out more. Bernoulli's pressure is the pressure against the walls of the pipe as it flows. So atmosphere and the pressure across this pipe right here at point D compared to the air, that's what's going to get it to flow. So that's if I had delta P for doing Poiseuille's. How much is fluid is going to flow? High pressure to low pressure, the bigger the pressure difference, the more that flows. A little bit lower pressure, a little bit less flows. A little bit less, finally Bartolini pressure. So that's what causes that. But the pressure against the wall of Bernoulli's, you're absolutely right. As it flows faster, which tube is more likely to collapse? One or A, B, C, or D? Which one is going to have the least internal pressure holding the walls open? This one right here. Because the fluid is going faster, as it goes faster, the pressure against the walls drops. And so I kind of want to change the cause and effect here. So why is it that bottom, greatest pressure, hold D, we have the high velocity, instead of low velocity, because the velocity is caused by the pressure difference from one end to the other. Now, pressure of the pipe is actually highest at D, isn't it? So how would your ears feel? You dove into this tank within the pipe here. I'm talking about within the column here. So at point D, C, B, and A, those are all inside the tube. So where would your ears hurt the most if you dove into a pool? If you went to point A, B, C, or D? Point D. The weight of the water would be crushing on your ears. So it's going to push out, but notice they're all open to the air. They're all open to the exact same atmosphere. So really high pressure and hard leading pressure, biggest delta P, minor pressure and air pressure, essentially relatively close, so low pressure difference. So that's why this one's flowing so much more. But within the pipe itself, the fluid's flowing faster through pipe D than it is pipe A. So pipe D has the smallest pressure against the walls. So it's the one that could collapse most easily. And so trying to distinguish the two pressures, Poisson pressure, pressure difference from one end of the pipe where water enters in to the other end of the pipe where water flows out. So that's the delta P in Poisson's. So I would use that one. I would use P at D minus P of air times pi r to the fourth over 8 viscosity L equals the Q coming out of pipe D. And so because this pressure gets lower and lower with each one, we get less and less. And so it's distinguishing these two. And I want to address this just real quick. A lot of times, and this I want to make clear, if you send something in that's really good, complex or easy is irrelevant. It's just, this is so common, and this is such a good picture you sent in. And I've talked to one person in chat. Nobody, I guess, no one knows who submitted this, but the point being, this is an excellent one. So something like this, I chose not to go by email because this is one of those, you found a phenomenal picture. And how many have experienced this just in life? When you have a jug and you let the water run out. So we usually put, you read the spigot at the very bottom. Like if you have a container with some, I don't know, syrupy fruit drink you're drinking because you're playing a sport or whatever. How many degrees it drains and drains and drains, it comes out slower and slower. Eventually you have to tilt it. The height gets less and less, the pressure D gets less and less and pushes it out with less force. But how many agree when you first open it, it drains really fast and less and less? This isn't actually in the text. This is somebody submitted from online. And so I think they got it by Googling. I don't know. But it's basically the idea of, have you ever had one of those like 2, 3, 4 gallon jugs that you put all that fruit drink into, or whatever you like, orange juice, whatever you're putting into it? And I don't know, is this a generation gap? But once upon a time, land far away called my childhood. Whenever we played a sport, we all got paper cups and this big container of whatever cheap drink they got from the store with mixing with tons and tons of water. How many know the thing I'm talking about? Okay, so if you experience it, oh, what? What is it called? Okay, so 2 people remember it, 3 people remember it. Yeah, Gatorade is one of the things I guess people put into it. Oh, the Gatorade powder, yeah. So this was, I actually played sports before Gatorade was prominent, before it like did its advertising campaign. But it was something basically rip-off version of Gatorade, cheapy version of it. But if you were the first one in line, you push the button and you agree a lot of it came out. Or a coffee urn, perfect example. When there's plenty in there, it comes out really fast. But how many agree as the height gets lower and lower and lower, does it drain faster or slower? How many have definitely experienced that as it gets emptier and emptier, it comes out slower and slower until finally you're getting the dribble? That's because the pressure at that point there, as the level gets lower and lower and lower, rho GH, as this drains out, gets lower and lower, that height gets lower and lower, it pushes less and less and less until finally when it's empty, they're equal. You had no drops wasted. Same with us. Yes, exactly. And so private question just popped up. So does that mean pipe D is most vulnerable to collapsing? Yeah. So, right, this one, you would worry about the fact that, one, the weight of everything can crush it, but number 2, because it's flowing so fast, as the fluid flows faster through that pipe, it hits the walls less, so it's at risk for collapsing. Yeah, and it brings up something. So good real life example you just asked about. If there are pipes, particularly like oil pipes are very common on the floor of the ocean. So when they dredge up this oil, it's easier to send it laterally. Yeah, you want those pipes, number one, be really thick. And number two, you generally don't flow the fluid too fast, because the faster it goes, the more it collapses. And you always want to reinforce your corners and turns, because that's where it does its weird non-linear forces. So you can get like low points of pressure. No, so hydrostatic pressure, although we see it in Bernoulli's equation, is actually the pressure pushing from one end to the other. So rho GH is PD in this case. And you have two Bernoulli's concepts going on. So if you want to talk about pressure against the walls and how fast the fluid's going down, weird thing, you could still do it. The top is going down, the bottom is staying stationary. So you have to have either a local speed or an average speed of the fluid going down. But you could measure the pressure against the walls. So in essence, yeah, we are kind of using Bernoulli's principle to say that the pressure is highest here because of rho GH. But I'm just going to take it as plain old hydrostatic pressure and say, I don't care so much about Bernoulli's except for pipes, pressure against the walls of the pipe. So do you read how fast this water comes out as a result of how much pressure against the walls or how much pressure from one end to the other? So the fact that this water squirts out so far is because it has a really high pressure here and air pressure here. So really high pressure is bigger than air pressure. So it pushes out a lot of fluid. A lot of fluid has to go fast to make it out. Does that make sense then, that Bernoulli's would be pressure against the walls of those pipes, not end to end? And it's seriously an easy thing to get twisted up. And it's because Bernoulli's is pressure against walls and Poiseuille's is end to end. And this concept is constantly distorted. And the truth is, I think some of you may understand it, but still get tripped up. How many fall in that category? I know it when I can visualize it and settle in on it, but it's easy to screw these things up. Yeah, so, okay, the thing is, Bernoulli's takes into account three pressures: pressure against the walls, kinetic pressure, i.e. pressure due to motion, collisions with the walls, and height. Hydrostatic pressure is a component of Bernoulli's. I cannot say this is Bernoulli's pressure. This is one of three components we use to calculate Bernoulli's pressure. And I'm not going to worry about it for now. I'm going to worry about it just being a static pressure here, pushing water out this way. The only spot I really would apply Bernoulli's would be through this pipe, through this pipe, through this pipe, and this pipe, because that's where fluid is flowing through a tube, which means it's moving, has velocity, has hydrostatic pressure, and therefore it has pressure against the walls. So I could apply it here, 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 and here, but from one end to the other, that's not Bernoulli's, that's Pascal's. That's Poiseuille's law and Pascal pressure. Yeah, exactly. Bernoulli's has three components: pressure against the walls, hydrostatic pressure, motion pressure, velocity pressure, whatever you call it. Hydrostatic has to do with the height, or in this case, depth, but exactly. So I could, if you really wanted to, I could tell you what the pressure against the wall is, but that's because it's not moving. So the pressure against the walls is just rho GH. Anyway, I think, honestly, I think the issue is trying to make more out of Bernoulli's than it really is. And this one really isn't a Bernoulli's question. This is really a Poiseuille's question. Small pressure pushing out barely moves. Medium pressure moves a little more. High pressure moves a lot. Super high pressure pushes it really far. So as you go down in a tank, the pressure gets higher, so it pushes the fluid harder and pushes it out further. That's really what this thing is coming down to. So hopefully that seems okay. Okay, so now you owe me an answer. Where do you bleed out more? Where do you have to have more factor VIII released or clotting would occur? If you punctured your earlobe, your elbow, or your big toe? So where do we release more thrombin naturally? It's in our survival mechanism. Big toe. Why? Yeah, exactly. The same thing here. You bleed out from your toe more than you do from your ear. We naturally release more thrombin when we puncture a lower point. Same story. Again, why do you elevate a wound? Why do you move a wound from here to up here? Decrease the pressure, pushing out. Yep, and the heart's working. So why do you lay a patient down? So that you don't have drastic differences here and here to level it out. They all fall in the same category of height corresponding to pressure. Okay, so works out perfect. This leads perfectly into this next question. Same concept, except now we have one spout here. So again, I have rho GH as my pressure here, where this is my H. What's interesting is here's my rho GH, and here is P of the surrounding air. Which is higher, pressure of the air or pressure of the fluid in the column? No? Which way is the fluid flowing? How many of the fluid is flowing out of the pipe here? Fluids flow from high pressure to low pressure, perfect. So I know this is my high pressure on this side. This is my low pressure here. But is pressure all or nothing, high, 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 low, 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 or is it high, medium, low? Is it a gradient? High, medium, low. You get a gradient. And so it ends up then that as it's going through here, let's figure out what's going on. It's moving down this pipe. The pressure as it drops degree is going to hit this opening. Is it possible that it can actually push some fluid up here? Sure, it's going to push it up a little bit. It ends up that if I did this right, and I'm going to hopefully draw my line correctly. Okay, I mean, I'm not going to be able to draw a line straight, but it should be this height. And as I go, so this one's probably visually a little too high. I mean, granted, my line sucks. It's not going to the middle like it should. But hopefully this seems okay. And this is kind of the reverse of the Venturi effect, because you're not sucking fluid up by creating airflow this way and sucking air out and pulling something up. Instead, you're pushing it up from the bottom. It's still a similar concept. It's still pressure disperses, but it's basically branching. As it goes through this pipe, it has a choice to go out the end here or go up here. So it's going to go up the pipe, up the pipe, up the pipe until finally the weight of the fluid per area, the hydrostatic pressure, is now going to cancel out the fluid flow pressure. So it basically pushes it up. So what should happen over time to this height as this reservoir drains? Oh, you know what I'm guilty of? I just realized what I did with this picture from before. I so sincerely apologize. I think there's my straight line that isn't so straight. So this would have been the height when we first start out. As a reservoir drains down, what happens to the height in this column? Go with instincts more than anything on this one. Why would it decrease? You're absolutely right. What makes you say that? Give me any intuitive reason you have. Perfect, because if rho GH decreases here, you have lower pressure here. So when high, medium, low, now it might be medium, medium, low, and low. As the pressure drops here, it's also going to drop everywhere in this pipe, push up less. Perfect. Number two, if this drains all the way out, is there any reason why this height would stay high or would also drain out? Yep, so if I put a plug here, if I shut this off, this is going to drain out too. So Two perfectly good reasons. Okay, now to figure out how to answer this question. So what is the question asking me? Ask me, what if we change the medium? So we change it in two ways. Number one, we change it in the mass and density. It's totally different density, or is it now the same density? How many agree it's the same density? Just tells me the same density. Because it's the exact same density, does that mean it's still rho GH? Even though I've used a different material, is it still the same rho GH at that point? So a couple things. Number one, it should have the same rho GH here and here when it's totally stationary. But one thing that'll happen is as it flows this way, because it's higher viscosity, it should flow faster or slower. Should flow slower, perfect. So it's gonna have a lower fluid velocity, so I can get rid of, oh shoot, I wanna change color. So it's gonna flow slower just because higher viscosity. Density and viscosity are not the same. And this is gonna be really lame to say this because it's not 100% true, but you wouldn't give it two distinct different common words if it was the same thing. So density is mass per volume. How much does it weigh in a given volume? Viscosity is resistance to flow. So a perfectly good example, oil is less dense than water, it has less mass per volume. That's why it floats on top of water, because carbon is less massive than oxygen is really what it comes down to. But its viscosity, for whatever reason, is significantly higher. Most oils, now this isn't true of all oils, but usually higher weight crude oils have very high viscosity. They don't flow very well, even though they're less dense. So yeah, viscosity is like fluid friction. Well, viscosity is basically how syrupy it is, how hard it is to pour. So the more viscous it is, the slower it's going to move down this pipe. Okay, the height is a rho GH phenomenon. It's still going to have the same, because rho GH is the same here, air pressure hasn't changed, you have the exact same pressure gradient you do before. Now, if we change the density of it, you might see some phenomenon, but in this case, shouldn't see much. If it flows a little bit slower, then the pressure against the walls might go up slightly, but it's not enough to, it's not going to compensate for what we're dealing with here. So hopefully this seems okay. That, yeah, ask away.
Can you hear me?
Yeah, I can hear you.
Okay. Oh, is there a way for me to annotate the screen or no?
I think you can. I don't have it set up. Go to your options, and I think, don't you do or don't have that option?
I don't see it.
Okay, let me see if I can do this. Let me hit more. See if this gives you, oh shoot. I'm gonna lose all my writing in a second. I'm so sorry. I'm just, actually, let me, oh cool. No, I just found a way to do it. Okay. Now do you have annotating abilities?
No, I don't see it.
Really? Okay. Oh shoot, I thought making you co-host. Yeah, I would have to go and exit out and go into my Zoom settings. So I'm so sorry. Yeah,
It's
I just,
okay. I'll just try
I
and
had it.
drive it.
Yeah.
Oh.
Didn't we have that going? Wasn't that something that worked before? Does
Yeah.
anybody have annotating on it?
Does mobile work?
Huh.
I can try and log on with my phone.
Yeah.
Yeah, I don't see on the computer either. I normally.
Yeah, so somebody said it was during my Zoom class we did it. I don't know what's different. I don't know if I made it because of waiting room phenomenon or what. Huh. Yeah. Oh, okay. Sorry about that one. Well, yeah, see if you can ask away and I can do my best to try to move my cursor to the right spot.
Oh, actually, maybe if I can just share my screen, maybe that would be easier. So I can annotate, so I can just show you my cursor, like where I'm at. Would that be okay?
Yeah. So what do I have to do? Do I have to exit my screen?
I think I can just share it.
Yeah, see if you can override mine. Can you?
Okay, let me try it. 1 second.
Yeah, I think that's true. I'm just going to stop my share. Okay, you should be able to share at this point.
Can you see this one? Can you
Yes.
see my screen?
Yes.
Okay, okay. So from my understanding is that the Bernoulli's only like it only goes like this,
Right.
and then put poise. I don't know how to pronounce the one that's with the P. The pressure goes like this. So at the top here for Bernoulli's, because it has the least rho GH, it would have the highest Bernoulli's pressure. Is that true?
No, see that this is what's kind of backwards about this. Is it's actually your hydrostatic pressure. It's the lower you go, and this is why instead of trying to make it an equation, this is where equations can throw you off. What happens to your head if you dive into a pool?
Oh, I see. So rho GH would be the lowest here.
Right, because it's the smallest from top to that mark is the shortest distance. As you go lower and lower and lower, you have a greater height of water pushing on you. So does that make sense then? So where your cursor is right now, your pencil, oh, now it's gone.
I moved it away.
But yeah, so always try to make a real life perspective on it. So the deeper you go into any tank of water, the more your sinuses hurt, the more your ears hurt, because you have a greater height of water above you.
I thought the equation was P plus rho GH plus I forgot, was it like 1/2 P
1/2 density V squared. Perfect.
something like that. Yeah. So if the height is like low here, then wouldn't this increase since the height is lower here?
Oh, yeah, but but that's if we're looking at pressure against the wall for a flowing fluid. Okay, so I mean, we have that. So does equal constant, so rho 1, yeah. So I need to jump back into this then. Yeah, it's just Bernoulli's doesn't apply here is basically what we're getting at for in this case. I'm trying to, oh shoot, you can't see my cursor, can you?
I think I have to, no, I can't.
Yeah, I didn't think so. Okay, sorry about that. Because yeah, let's see if, I don't know if I have, nope, I can't do anything either as far as annotate. Because I'm trying to show like on the walls. So you're right if that's equal to some constant, some equation. For if the fluid stationary, there is no velocity, it's just sitting there. Pressure against the walls, as H goes up, pressure against the walls is going to be greater. But that's just that hydrostatic pressure. And that's why Bernoulli's isn't really applicable here as much as it is just good old-fashioned hydrostatic. The key word there being static. Whereas Bernoulli's, you have a velocity. So you have pressure against the walls as it's something's flowing through a pipe. This, what you just described, what is flowing through the pipe?
Nothing, so this would be 0.
Right, and therefore that pressure doesn't work. So Bernoulli's is for pressure against a wall when something is flowing. So when everything is stationary, it's no longer Pascal's or Poiseuille's, no longer Poiseuille's or Bernoulli's. It now falls under something called Pascal's principle. Pascal's principle is pressure will level itself out to balance so that you get no pressure difference. So Pascal's would tell me the pressure outside and the walls pushing in on the fluid equal the pressure of the fluid pushing out on the walls because it's not moving. And would tell me the pressure is uniformly distributing through the material. But hydrostatic pressure, when you go into that medium and you start descending through it, your ears definitely hurt because of hydrostatic pressure. So apply Bernoulli's to a moving system, to something flowing through a pipe. You have to have air that's moving. You have to have water that's moving, you have something that's moving. Hydrostatic, just apply simply the hydrostatic gauge pressure, rho GH. And I don't know how to explain it other than you have to apply the corresponding equation to the correct system. And I think the easier way to consider that is to just visualize it. Nothing's moving, so it's just rho GH. If it is moving, then we suddenly have rho GH and 1/2 rho V squared and pressure against the walls to consider. So I don't know if that helps or not. I don't think it really helps that much other than to say it's stationary. So use a stationary hydrostatic fluid equation.
Do you think we could discuss more about this like after lecture today or after?
Maybe, yeah, maybe we can. I have, after this, there's still 19 questions to go. So I don't honestly, realistically, probably won't be time. We can definitely revisit it at some point, but I think in the interest of fairness across the board, I'm gonna.
Yeah, okay. Thank you so much.
Yeah, you're welcome. Yeah, I just got a couple suggestions to move on. So sorry. I will get rolling on this. My apologies. Let me share this again. And then we'll move on to the next one. So and sorry if it didn't come across clean, because as I'm sitting there listening to myself do it, I realize I'm just not explaining it well, other than the key thing is, oh, sorry, shoot. I don't have my chat set up. My apologies. Okay, now we're good to go. Is it, if it's stationary, use stationary fluid. If it's moving, use a moving equation. The moving equation being Bernoulli's. Yeah, and somebody asked, height is the depth of the column. The deeper you go, the greater the height of water above you. That is what it comes down to. Okay, moving on to this one. So for this one, I want to try to do as much as I can intuitively before I ever start breaking out equations. So first and foremost, which is less dense, the blue one or the green one? Why the blue one? Floating on top. They're immiscible. The one that floats on top is less dense. So can I, at the very least, get rid of A because of that right there? Okay. And then the next thing, this is purely intuitive. Before I do any math, I want you to tell me about the values. A over B. Is A small and B big, or A and B about the same amount? What do you say? A small, B is big. So can I say that's a small fraction? That's a small fraction. And that's a big fraction. And just to put it in perspective, what I mean is this is less than a half, more than a half. Okay, that's an intuitive thing. Would you agree this amount of water, or sorry, this amount of Z, excuse me, water's usually blue, not sure why I color coded it this way, sorry. But this amount of Z seems to be roughly equal to this amount of water. Would you agree? Because the Z wants to go this way, the water wants to go that way. So can I say that this amount of Z and this amount of water are offsetting one another? Is that, do you agree with this? This amount pushing here and this amount pushing there. If it's not moving, they must be canceling one another. How many combine to that they're both holding each other in place? Meaning if I took away this amount of water, it would flow over. If I took away this blue, it would flow over this way. But if this stays here and this stays here, do you agree it's going to hold the other one in place? How many just feel that, believe that intuitively? Okay, if you don't see it, I'll feel that in a second. But for those who do see it, then what do you know about this? Would you grade this amount of blue and this amount of green are drastically different or relatively close in quantity. So how many grow this one? They're different by a lot or a little. They are different, but is this a lot more or just a little bit more? And this is, no, not the whole amount of green, the amount of blue that's holding it here. So, okay, you know what? Is this working for anybody? I'm hoping, and the reason I'm asked this, I want honest feedback. If it's helping nobody, then I'll go down the traditional math pathway. But what I'm hoping is somebody trusts their instinct to say that this amount of blue is pushing this way, this amount of green is pushing this way. I don't care about the bottom. So it's almost like this part isn't even there. I don't care. That's holding it up. If these are roughly equal amounts, this is more, I know, I see it, we all see it, but it's kind of only a little bit bigger, which means their densities are drastically different or actually kind of close. Kind of close, which means what I need to multiply the density of one by a fraction less than a half, or more than a half to make them equal. What your intuition tell you that the best answer is, just visualizing it. A number more than half. How many, this is a weird way to put it, but how many feel that D is a good answer? Okay, yeah, and I mean, I sure as heck don't want you to feel things on the MCAT. You'll be insane. But if you lean towards D, now let's do it math-wise. So I'm going to support this same notion, but I still want to at least have a biased opinion to start out with. So I'm going to clear everything. And again, I'm going to say that's wrong. So that one's out. And then I'm going to make this comparison. I'm going to say that P atmosphere, column up here, open to the environment, plus rho GH1. I'm using 1 for Z and 2 just because it ended up water and Z didn't fit in my space. And then this for that. So I'm basically getting rid of this part right here and just comparing this to this. Atmospheres cancel. And then G's also cancel. And so we're left with density H equals density of H. They're looking for the density of Z, the density of 1, as I've set it up. So I'm just going to divide by H1. So in doing so, the density of 1 equals H2 over H1 times density of 2, density of water. The relative densities are B over A plus B, because the relative height is B for height 2, A plus B for height A. So that's the fraction I need. That one fits into that relationship. Okay. I'm going to throw this out to everybody. How many, when you look at this, think this is Bernoulli's equation? So would you apply Bernoulli's equation here? Anybody? It's not moving, exactly. It's stationary, so I think we need to be careful thinking Bernoulli's is really cool and really wonderful. Bernoulli's is very specialized. Wings moving through air, sails moving through air, pipe moving, or fluid moving through a pipe, moving fluid, but when it's stationary, rho GH, rho GH. Yep, and rho GH, again, that small part is one of the 3 pieces in Bernoulli's equation, but it's stationary. A fluid is defined by particles that can move. Not that they have to be moving, but they can move. So yeah, air is a fluid, atmosphere is a fluid, water is a fluid, any liquid and any gas is capable of movement, therefore it is capable of flowing. But in order to flow, you have to have a pressure difference, but absolutely right. Okay, so does this make sense mathematically, why this fits? Yeah. Okay. Again, I keep on getting stuff from Bernoulli, so let me at least address that. You're absolutely right. How many learned for the total energy of the system equals some constant equals the kinetic energy, 1/2 mv squared, the potential energy, mgh, and work, force times distance. How many learned that equation to be true? Conservation of energy says work plus kinetic plus potential equals some constant. Energy is conserved. You can convert kinetic to potential. You can do work on something and give it potential. I mean, how many have definitely seen this equation at some point? That the energy system is the work done on it, plus its kinetic, plus its mg. How many have definitely seen that? All we do is we divide everything by V, and guess what? We are now Bernoulli. So let's figure out what happens. When I get rid of the distance, that's an area. Force per area, pressure. Instead of mv squared, it's rho, 1/2 rho v squared. Instead of mgh, it's rho gh. So yeah, this looks an awful lot like another equation you've seen. It's the exact same equation, but now divided by volume. All Bernoulli did is said energy is conserved. If you do energy conserved in a constant volume, then you can say those things also have to balance out. That's the energy for total. This is the equation for total energy of the system. The total energy of a system stays constant. Total energy of whatever we're looking at. Okay, but yeah, and again, this is just one component of all three that are in here. So Bernoulli's equation is really cool, but it doesn't apply to all that many things. It applies to fluids in motion. So for hydrostatic, just go with the hydrostatic portion, stationary fluids. Okay, want to move on from this. Because if you're right here, so the question is, where did P atmosphere come from? If you're right here, actually, let me pick better colors, sorry. If you're right here and right here, what is everything pushing down on you? There's the column of the fluid, would you agree? Check. But is there also air above you, or are we under a vacuum in this system? So on this side, atmosphere plus this column, and on this side, atmosphere plus this column. So that was pushing down and pushing fluid that way. This is pushing down, pushing fluid that way. Not the total pressure of the system. It is the total pressure you feel above your head. If your head is right here, it is what's pushing down on you. And if your head is here, it is what's pushing down on you. So let me ask you this. When you go to the mountains, does the pressure feel different? Sure. When you go underwater, does the pressure feel different? Yep. So atmosphere is basically rho GH of the air plus rho GH of the fluid, the liquid. If you go in the mountains, you have less air, so it feels less. Go lower, you get more air. But you can definitely feel pressure from the air surrounding you. Otherwise, when you went in the mountains, you would never notice it. But when you go to the mountains, you can definitely feel a change in atmospheric pressure. So the pressure at this point is everything above it in the entire world as we know it, the system of our planet. The column of fluid, liquid, and the air above it. Air plus liquid equals air plus liquid because this is pushing down and this is pushing down equally so it doesn't move. Poiseuille's is for a moving fluid. Q is the volume flow rate, how much moves, so yes. So the question was popped up. So rho GH is for a static fluid. Yes, 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 and yes. Bernoulli's is for a moving fluid. Yes, because we have fluid moving through a pipe or air moving across the surface, we have motion. Poiseuille's is for end-to-end motion, but not velocity, but volume that's moving. So moving fluid, pressure against the walls, Bernoulli, pressure from end-to-end, Poiseuille's, stationary fluid, Pascal's principle, and hydrostatic pressure. Just we'll apply it as we see it. Okay. Yeah. Question or? Okay, I'm moving on then. On to GChem.
Oops.
Okay, so fine to move on. Okay, we're moving. For the following equilibrium reaction, what is the effect of increasing the external pressure? Ooh, sorry for my bad spacing on this one. So if we increase the pressure around it, what are we doing to this equilibrium? Are we pushing on the equilibrium in one direction as opposed to another? It's like adding a reactant. Perfect. Why do you say that? You're 100% right. What's your perspective in coming up with that conclusion? Three gases. Perfect. Two gases. So when we squeeze on a reaction, we press it down, what's it going to do? Move to the side with more gases or less gases? It's got to go to the side with less gases. That's the Le Chatelier's principle. So in that case, what would happen to the moles of sulfur dioxide? They would go down. So that's true. What would happen to the moles of oxygen? They go down, that's false. What happened to the moles of sulfur trioxide? They would go up. Making that statement false. And then what would happen to the equilibrium constant? Perfect. Why is there no change? Only changes with what variable? Temperature. So perfect. Okay, free to go on, move on to this one. Okay, so let's revisit. I'm gonna quote this sentence. I'm gonna see what, if anybody can pluck off what's off in this one. Sorry, come on. I thought when you increase the external pressure, all moles of product and reactants increase. So there is one word off in your sentence. If we increase the pressure, what goes up? Moles, temperature, volume, or pressure? So if I squeeze on something, if I push on a balloon, push harder and harder and harder, do I make more moles or do I just make more pressure? You're absolutely right. The pressure of everything goes up. When I increase the external pressure and compress that system, all these pressures are going to go up, 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 up. But do the number of molecules increase or decrease? No, the moles are still the moles. They're just more crowded now. They're going to collide more often, but the moles are the moles are the moles. But when it goes this way, the moles move over. Yep, exactly. More pressure means more collisions, and considering collisions, 3 collisions compared to 2 is going to push it that way. So do you see what the difference was there? Moles and pressure. This specifically said moles. Okay. For this one, water shift reaction has an equilibrium constant close to 1 at elevated temperatures around 1100 K. If the reaction were at 10,000 or 1000 K, 1000, sorry, what would be expected if the pressure of the system were lowered? I have no idea what that means. So we went to a different temperature. Is that even relevant? Not unless I asked about 1000 K compared to 1100 K. Exactly. So if the reaction were at a different temperature, what would be expected if pressure of the system were lowered? If I lower, increase, do something to the pressure, do you agree it's going to move to the side with more gas or less gas? Perfect. So if I lower the pressure, move the side with less gas, it would fill up the space. It would like re-equilibrate that pressure drop. So which side has less pressure? Which side has less gases? Reaction won't move because same. Okay, so I want to answer this one again. Does K-equilibrium change when we change the temperature? By all means. When I went from 1100 to 1000 Kelvin, yes, it definitely shifted and the K-equilibrium definitely changed. Is that what the question's asking? Or is that minutia tossed in there to screw with you? Is this completely irrelevant information? So is this just tossed in there just to screw with you? This completely useless first sentence, does it tell you anything you need to know what's going to happen if you lower or raise the pressure? So would this first sentence qualify as useful or is it a distractor? It's a distractor. It's just there to give you useless information. So the reaction will not shift. Do they ever do that? Does the MCAT really do that sort of thing? Do they actually give you distractors? No, okay, so the direction of the reaction there is no direction of the reaction. You have two gases and two gases. The point is it's not moving. If something is not moving, there is no direction. I can't say it's not moving forward, not moving backwards. It's just not moving, if that makes sense. Same number of gas molecules, 2 going to 2 isn't going to relieve the pressure. Yep. And then how many read what Michaela tossed in there? How many agree about 2/3 of every passage is kind of minutia? And every now and then there's a question that has a sentence or two that's complete minutia to begin with. Useless information just to throw you off the scent. That's exactly what this first sentence is. It's useless to me. So important that we can zero in on that. Okay, hopefully this is okay. Yep, if there's more moles of reactant than product, so if you start with, let's say, 3 going to 2, like we had in that other one, lowering the pressure would move it in the reverse direction. So if that makes sense. So if I went from 3, like if I go from 3 gases to 2 gases, if the pressure went down, I lower the pressure, it's going to move in a way to re-equilibrate, to increase the pressure. Equilibrium constant stays the same. Different distribution, but the same mathematical total. Okay, this one is just flat out a trick question. So which of the following starting conditions results in the greatest amount of H2 at equilibrium? So what I want to do is I'm going to put everything in here and say, I don't care, I don't care, I don't care, I don't care. Why do I not care about the BR2? It's a liquid. Liquids don't impact that equilibrium, only the gas does. So in choice A, I have 0.8 in excess. In choice B, I have 1.0 in excess. In choice C, I have 0.8 in excess. And choice D, tell me where the heck I'm coming up with the fact that I have 0.5 in excess. Where the heck does that come from? That's kind of weird. Yep. Why is it half an atmosphere? Why am I putting that here? Why am I changing this one? Because there's 2 HBRs. So basically it comes down to this. I want to compare everything equally. I compare reactant, and product. Product's a weird one. So I'm going to say, what if all this HBr went back this direction? So that's a question about equilibrium. If you start with all reactant and go forward, it's going to be the same equilibrium if you start with all reactant or all product and went backwards. It's equilibrium, no matter what pathway you take to get there. Yeah, doesn't really matter. So because there's one atmosphere total, and I need 2 of these for every one of these, and if it went all the way backwards, 1 atmosphere would turn into half atmosphere. So the question comes down to which is going to give you the greatest amount of H2, starting with 0.8, 1, 0.8, or 0.5. Which one is going to result in the most H2? The one that starts with the most H2. So if you start with 0.8 and it goes forward, start with 1, it goes forward, start with 8 goes forward, and 0.5 go forward. You agree if you have more to begin with, you're going to have more of everything. If you have less to begin with, you're going to have less of everything. So why aren't we counting this too, is you're asking for? We did when we came up with 0.5, because isn't that kind of what we're saying in this one? So, yeah, so I mean, it is 2 HBRs, but it's asked for the greatest amount of H2 gas, not hydrogen atoms, but actually H2 as a molecule. So that 2 there means I'm not splitting into which has the most hydrogens, it's which one is the most H2 total. So yeah, so I mean, why am I saying that if I have 1 atmosphere to start out with? So choice D, if I start with 1 atmosphere here, and it goes this way, why am I saying it's only 0.5 atmospheres? Because it's a 2-to-1 ratio stoichiometrically, and I need 2 H's. I need 1 H from one HBr and 1 H from another to get this. So I have 1, I can only get half. So hopefully it seems okay. Perfect. And then in this case, the one with the most to begin with is the one that's going to be the most distributed across the board. So the best answer is B. So this one is kind of oh, you're welcome. So this one's a little bit on the tricky side. So I'm going to explain the reaction of 1 atmosphere of HBr and 1 atmosphere of H2 results in no change. Didn't we just get done saying, I don't care about liquids? All of a sudden, I'm caring about liquids, and I'm not sure why. So you're going to have to help me out. So I have 1 atmosphere, 1 atmosphere. How much Br2 do I have? Zero. This one you don't have excess. Normally we would, but in this case, there's nothing. So all of a sudden this went from excess to now the limiting reagent. So can a reaction, oh, so why? Let me ask the other way, where in the question do you see that it has HBr? Or I mean, or H2 and HBr. They tell you it has HBr, check. They tell you it has H2, check. Where does it say that you have Br2? So therefore we don't have any, because they say mixture of these two. So I mix these two together, but there's no Br2. So what would happen if you had a little Br2? Good question. Let's figure this out. So when it is at equilibrium, we have something called K. When it's not at equilibrium, we have Q. So Q in this case is going to equal HBr squared over H2. And I apologize, I'm putting brackets, but I don't want to put pressure. Doesn't really matter because thankfully they're all ones. And then K equilibrium is equal to, in this case, 2.72 times 2.72 over 1.36 product squared over reactants, ignoring the liquids. Ends up, that's a 2. So this equals 5.44. So which is bigger, K or Q? Which one's bigger? K is bigger than Q. Take the greater than sign and turn it into an arrow. To reach equilibrium, it would want to shift this way. So if I had a little bit of BR2, would it be able to shift forward? If I wasn't completely out of BR2 degree, it would want to go forward. It wants to shift, but it can't shift. So does that make sense? Does that field your question? So good question. What would happen? It's just stuck. It's stuck at Q, exactly. Can't go forward because you don't have the other thing you need. So you can't make a meal if you're missing one of the ingredients. So hopefully it seems okay. So is this a trick question because it was a limited reagent? So now what is the best answer? Is that equilibrium? Nope. One is not 5.44. That would be at equilibrium. That's out. Can't go forward because choice B. So this is actually right up their alley. I'm actually pretty happy with this question. Okay. No worries. I mean, this is, the thing is, and just feedback from everybody, how many of these questions, A, were your questions at one point and when you went through these, and how many are you recognizing from previous office hours? These are, they're all good questions. Do not apologize for having questions ever. And I say that because about 3 of you have said that so far today. So, I mean, just that's why you go through these things. And how many learn more getting beat up by questions than anywhere else? Yeah, actually, can I quote you on that? Just what just popped up, last thing in chat. And how many would agree with this sentence? Does this describe your homework perfectly? I did well on the phases, but these minute things bother me, and they're costing you a question here and there. How many find when you go back and look over things, it's always a pissy little detail here, a trick question there, careless mistake somewhere along the way? How many realize it's the little things, the polishing, avoiding careless mistakes, recalling that one random fact that you knew once upon a time and it's lost in the abyss, but it's back now? Those are the things that matter. Don't freak out. Okay, so given that pK is 5, what is a pH for 100 milliliters of this? Is 100 milliliters relevant? Nope. So the way we get the pH for a weak acid, I'm going to go with my curve again. If we were strong, it would have been down here and look like that. It doesn't. We get this number right here by averaging pH and pK. So if it were a 0.1 molar strong acid, what would the pH be? So if it were strong, what would the pH be? So I don't want a general answer. I want actually a very specific answer. So if I had 0.1 molar HCl, HBr, HNO3, some strong acid, you agree it would fully dissociate. This would be 1 times 10 to the minus 1. So log 10 to the minus 1. Log cancels 10, minus cancels minus. It would be 1. So the pH right here would be 1. And then the pKa they gave me is 5. So what's this number in the middle then? So cool little shortcut equation for getting the pH of a weak acid. The pH of a weak acid. Oh, I'm not, and I want to respond with this. I'm trying to figure out the way I'm going to say this is going to sound really mean, and I don't mean it to sound mean or impolite, but I seriously, I don't care if you don't understand why I'm averaging them. And I want to explain why I'm saying that sentence, because it's rude and condescending and it comes across wrong. But that's because it is a derived equation from the icebox I did earlier, and I do not want you to do derivations. I want you to just trust that the derivation, derive it one time, come up with it, and just trust that after doing the icebox and plugging in, it is not the aha equation. You don't have ah, you only have ha. So you cannot use aha when you only have ha. It is, I mean, hate to say it, it's named the Bennett shortcut equation. It's one that's buried in there, and it is basically the pH of a weak acid equals the pH, if it were strong, there, and the pKa there over 2. You're averaging them. You average them because I went through the icebox and explained and came up with it one time, derived it, and we said, good, we believe it. So I ask you, do you ever question why we do this? Have you ever asked that same question that you just asked there and understand why you were averaging them? Did you ever ask the same thing, why you're averaging them? We derive it one time, we believe it, and we just say it's symmetric. So it ends up, it's a symmetric thing. It's been derived one time, it's now a memorized equation. And so again, I apologize for how condescending that sounded, but I'm trying to emphasize at a certain point, you just got to trust that this is symmetric and this is symmetric, and we can average it, just like we can average pK1 and pK2 to get that point because it's symmetric. So hopefully that seems okay. And how many do remember this equation popping up in the lecture, that we get the pH here by averaging pK 1 and 2? In fact, can I erase everything in a second and show you like the big picture, what I hope you believe? Free to erase? Okay, so if I have a curve, with something like that, I want you to recognize pK1, pK2, pK3, pK4. I want you to know that this is an average of pK1 plus pK2 over 2. This is an average of pK2 plus pK3 over 2. This is an average of pK3 plus pK4 over 2. How many are okay with those three? How many have seen those enough to just totally believe these? I accept these because curves are symmetric and they've told me so many times, I'm brainwashed, I get it. I want you to also know that the pH here is pK1 plus pH of a strong acid of equal concentration. So if it were strong, and I want you to note that the pH up here is pK4 plus pH of the titrant over 2. These are the two new weird ones to add, but can I get the pH pretty easily at 9 different points? pK 1, 2, 3, and 4, got it halfway. pK's equivalent points in the middle, average of your pKa's, pK extreme, pK and pH with strong acid, pK, last pK plus pH of the strong base. So it is, I mean, how many are just programmed that you believe those things? Those are calculation truth. Take the time to summarize that. And hopefully this is just, I mean, in looking for some feedback, did anybody see this as an easy question because you remember this equation? So honestly, how many have done this? You're caught up enough on homework? Good question. If we're strong, let's mess with you a little bit. Let's say this was 0.5 molar. Then what would it be? Oh, that'd be 5 times 10 minus 1, so 1 minus log 5, which would be 1 minus 0.7, so it would have been 0.3. So it would have plugged in 0.3 into that equation. So it depends on the concentration. Just like up here is a pH of the titrant base always 13. Now it might be 13.3, 12 point something. So it's not always the same thing. But if you plugged in 1, you're going to be pretty close most of the time anyway. But hopefully it seems okay. So big picture, how many are okay with this massive curve with information overload? There's a ton of information on this, and if you pick the right points, you can actually get the pH incredibly easily when you start seeing this as just a summary of pHs. Okay, oh shoot, I fat fingered it. Hopefully, okay, good, it's still here. So if you need to screenshot it, feel free. You don't use it. Okay, and again, just I'm trying to figure out how to word this, but something that happens, it's real easy to do, is you want something to fit what you know, rather than taking what you know to fit it to what it is. So if you're trying to make this into the Henderson-Hausbach equation, the little bit you get when it associates is not enough. You are not at a buffer here when you first mix it. You don't get a buffer until you're here. So you cannot get to the buffer region, can't get to when you use Henderson-Hausbach by just adding this. You have to either add in its conjugate base, or you have to add in a base to remove the proton and turn it into the conjugate base. But if all you're adding is this one, Ha, you can't use the AHA equation because you're missing Ah. If you only add Ah, yep, the Henderson-Hausbach is only when it's a buffer, because a buffer has Ah and Ha. This is the only spot you have aha, 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 aha. Nope, 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 and nope. But yep, 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 and yep. When it's flat. Exactly. So what you just said, nope, yep, nope, yep, nope, yep, exactly. Steep ones, nope, nope, nope. Flat ones, yep, yep, yep. Henderson-Hausbach is a stupid name for it. From now on, you should call it the Henderson-Hausbach buffer equation, because it only applies when you have Ah and Ha, both parts of a buffer. And I think that's part of chemists naming things after themselves. It's sort of silly. We shouldn't do that. We should call it what it studies. Okay. For this one, anybody want to give me a hint what's going on in this? I have no idea when I look at this table here. So anybody want to tell me what's going on? Basically, I'm tapping the previous question for some of you who did number 11 or 13 help. Which one is an acid or which one is a strong acid? This is titration, exactly. So tell me about the 2 types of titration curves you're familiar with. That one is strong or weak that I just drew. I actually want to redraw that, just a little more anal. Why do you say it's strong? No lip, perfect. Which one is weak? Has a lip, perfect, okay? So let's consider the start of the curve, because that's where we decide. So from 0 to 5 to 10 is kind of your start, because it's only going to 50. Did this one change a lot or a little at first? In the middle, it changed a lot or a little? So where's the bigger change? In the beginning or in the middle? I don't know. If I do the math here, how many agree that's 0.67? In the middle, it's only changing by about 0.18. How many do believe that 0.67 change is bigger than 0.18 change? So let me just put the changes here. This one's changing by 0.18, 0.18, 0.67. Would that describe a change and a flattening out, or flat in the beginning? Which one? That one's weak. Okay. Second question. Is this changing by a lot or a little? So what's true of this one then? Is this strong or weak, would you say? Perfect. This is a strong acid because it doesn't change much in the beginning. So acid B is a strong acid. So is that basically what this question is asking? Which one's strong? So help me out. What can I get rid of? Those two are weak. There's two strong acids. Which one is correct? Why B? You're absolutely right. Why? It's not diprotic. It has a pH of 7 and equivalents when it shoots up rapidly. So it is weak, or excuse me, strong, and it is monoprotic. Hopefully it seems okay. Because it's 7. So how do you know it's monoprotic? Because that 7, if it was diprotic strong acid, second proton would also be coming off. So if the second was here, then this has to be less than 7 because I have a second pK too. So it's just one of those weird sort of, just you know that it's symmetric around 7 only if it's monoprotic, which this one is. If it's monoprotic, that only way I would know that. And that is important. I mean, because you could definitely get down to A or B, but sulfuric has this weird sort of second proton, so it ends up first equivalence point is less than 7. Okay, and that's so perfect. You did everything you should have done, and then it's just a matter of just recognizing the 7. Which is not true. So for diprotic acid, you have 2 protons. PK1, and then HA can protonate PK2. So going backwards, this is PKB2 and PKB1. True or false? Have I gotten that correct or incorrect? Incorrect. Why? Kayla, what have I done wrong? How do we name our PKs or PKBs, excuse me? Opposite PK. The first one off is the last one back on. The last one off is first one back on. So this is PKB1, first one back on, PKB2. Somebody had a great phrase the other day to describe these PKs and PKBs. So I'm going to show it for just some out of control case. Let's say pentaprotic. Those are my PKs. My PKBs would go the exact opposite way. So anybody want to chime in what your awesome phrase was the other night for how to look at these? That's going one way and the base PKs going the other. Oh, nobody's going to come repeat it? Anti-parallel. Isn't that what somebody was saying? Like, oh my gosh, the PK and PKB relationship is anti-parallel. One goes up as the other one goes the opposite way. It was great, but nobody remembers it. So how great was it? Who came up with it anyway? No one of you proposed it. It was genius. Jonathan, was it you who came up with it? Yeah. We're here with Jonathan, and you don't even remember your own genius thing? Oh my gosh. I don't know what the opposite of a star is, but yeah, definitely no star for you. Very disappointing. But anyway, yeah. So, yep, the invisible star, the anti-star. Okay, So is this a true relationship? Does pK1 and pKb2, does that combination add to 14? Sure, conjugate pair. Does B2 and A2 add to 14? Nope. Here's the kind of a tricky one. Let me just do the math on this. If pKa1 plus pKb2 equals 14, what if I cross this out and put in pKa1, or pKb1, excuse me. Is pKb1 higher or lower than pKb2? I forget, which is lower? These go up this way, so these must be going down this way or up the other way. pKb1 is a lower number than pKb2 because it's more basic. So it's a lower number. Because it's a lower number, this number is less than 14, makes that true. And is pK1 less than pK2? Is that just by definition? First proton off, the first proton's always more acidic. So that's a true by the rules of chemistry. Okay. Clicking on. What is true for the titration shown in figure 1? Okay. A greater amount of base is required to progress from the start of the titration to the first equivalence point than first to second. So is that true? Why do we call these equivalence points? Because basically I need to have the same mole amount. So first mole, second mole. And I'm putting mole there. It is not always a mole, but I'm going to say that. So that would mean this is false. Would you agree? The same amount. If you have 1 mole of acid, you need 1 mole of base to take off the first proton. You need 1 mole of base to take off the second proton. Okay, does that help me at all? In fact, is that actually surprisingly helpful? Perfect. So help me out. What can I get rid of? B and D are gone. Does that mean this automatically is true? Sure. And that's because the pH here is not equal to the pH here. So I need an indicator to be roughly equal to have pK equal to this one. I need a pK for this one. Yep. So equivalence point, you can only have an indicator pK equal to 1 pH. So if the indicator is 6 and this is pK 6, works perfectly. But if this pH was 10, pK 6 would not work. You have to have a separate indicator for each point it's indicating. Is there an indicator? Is there a single compound you know that has multiple color changes? So is there an indicator out there that goes from blue to red to green to orange to lavender? It'd be so cool if there was. The universal indicator, the thing they show you, is actually multiple indicators mixed together. So in theory, it could work, but really you could only have, it would have to be this weird sort of thing where, let's say it was red going to blue, going to yellow, maybe back to red. But in theory it could, but we just don't have one of those. Okay, last but not least, the pH of the first equivalence point can be greater or less than 7. The second one must be greater than 7. Well, I think so. Let's figure out how this works. The second one, do you agree, is going to equal pKa2 plus pH of the titrant. The titrant is always a high number because it's always a base. So it ends up, because this conjugate base, it definitely has to be greater than 7. So that definitely, this one, that's definitely true. Can the first equivalence point, how do you get the first equivalence point? First equivalence point you get by averaging pK1 plus pK2 over 2. In theory, can both pKs be low, 2 carboxylic acids? Could both pKs be high, 2 amines? Could one be high, one be low? And it ends up, maybe it's around 7-ish. In theory, because you're going to have different pKs, can you have a different first equivalence point? Meaning, can be greater or less than 7. That is true. Making C your best answer. In the answer explanation, it says challenge question. What the heck does that mean? If you run into that phrase, means it's hard and meant to make you miss things and learn from it. It's okay if you miss, exactly. Does that help any of you emotionally to know that there are certain questions and they're designed to screw with you? So hopefully so. So this is one of those where challenge question is basically my way of saying, I'm so sorry to put this really mean, evil question in here, but it's a really good, like, big picture thing. This one's locked in being greater than 7, but this one can fluctuate because pKs can fluctuate. That was the message being sent. Okay, last but not least, venous blood, around 7.2. So we have a couple equations here. We have apparently carbonic acid, where they want to know about bicarbonate, carbonic acid, and carbonate. So I need to write both of those relationships. The pK for this one is 6.4. I'm going to put this in here and I'm going to cut it off the chase. I'm going to put a number in here and you're going to say, do we have to memorize it? No, but you should know every proton's different by about 4 to 5. So if the first one's this, the next one would be around 4 higher or 5 higher. Just one of those rules of thumb. That's basically how I'm memorizing these things. I'm just going to put around 12 because I don't know it off the top of my head, but I know it's in that ballpark. So let's figure out what's in the highest concentration. At a pH of 7.2, is that going to favor the base side or acid side of that equation? .2 degree is higher than 6.4. So perfect. It's going to favor this side of the equation. But degree is going to favor this side because 7.2 is less than 10.8. 7.2 is higher, although barely. It's going to favor that side. 7.2 is less. It's going to favor this side. So choice A, is this compound in higher concentration than this? True. Is this in higher concentration than that? True. Is this in higher concentration than that? Nope. Is that my false one? And is this in higher concentration than PO4? True. I'd say carbonate, yeah, essentially 0, because I could say 10.8 minus 7.2, do you agree, is 3.6. 10 to the third is 1,000. 10 to the fourth is 10,000. So I'm going to say it's essentially 0, when in fact I should say it's about 1 out of every 7,000. It's so minimal. It's trivial amount. So there's a tiny bit, but not enough that we could detect it. So the best answer is that one. Hopefully this seems okay. All seems well. Okay, so shifting a little bit. These all come out of the practice test. So this is phase 1 practice, or phase 3 test 1 from book 1. So if you've yet to do this, And this is a judgment call on your part. How many realize you just don't have enough time in your schedule to fill everything in? No way. So if you were giving up on phase threes, which honestly isn't a bad plan, you should definitely do AAMC before you do phase threes. And if you have time, phase threes. I know a lot of you are going to end up shopping for UWorld. UWorld is really good for cars, really good for psych soc, decent for bio. 90% of it's really good for bio. 10% is kind of over the top and demoralizing. For chem physics, I think phase threes are better than UWorld. So if you have time, great, do them. If you don't, then I mean, don't stress about it. But this is basically in advance saying if you're going to do phase three, then I'm going to ruin it for you. Yeah, so it is my opinion based on feedback from what students have done in the past that for psych soc, UWorld, thumbs up. For cars, UWorld gets a thumbs up. Jack Weston gets a bigger thumbs up, but they're pretty good. For bio, UWorld gets a 90% thumbs up, a 10% FU. There's about 10% that are just like questions are just from so overkill and just punishing. And then chem physics, UWorld is good, but there's better out there. Alternate for bio, anybody want to toss their concept out? How many have heard of anything else pretty good for bio? And here's what I've read online. How much of that is spot on? I've heard Kaplan's biochem book is pretty good, but there's no real questions in it, just good for review. Princeton, I've heard mixed reviews. Some are really good, some are not so good for bio. And then for UWorld, the thing that this is what I've heard and what I conclude based on that. I knew a couple people actually when their team was writing about 10 years ago, 8 years ago or so, when they were really getting into getting this thing up and running. It ended up that they were hiring med students, and the downside is med students were enough removed from what undergrad was and had been, their head has been filled with so much med school information that every now and then they just did an overkill. It was just too hard of a question. But if you can emotionally deal with that, it's good to go. If you can just say, it's one of those damn questions from some anal person studying for their boards, it was over the top, you'll be good. So anyway, I mean, and how many have found, especially our physiology book, how many have actually found those passages to be pretty good? The physio book. Yeah, it's memorization based, but actually, I think it's pretty decent. I mean, that one I think is, I wouldn't really farm too far outside of that. Yeah, oh, Spencer is awesome. Spencer cares. And by the way, and again, I think you guys probably already know this, but I know Spencer is planning on doing a couple more lectures. I know he's doing a mop-up for genetics and a mop-up for, is it genetics and cell, I think, are the two he's doing a mop-up for. 3 years ago, is that, how recent is 3 years? So he sounds like a kid because he actually started, yeah, he started really, really young. Oh, yeah, all I can say is, I mean, without going too much personal life, he had to grow up faster than a kid should. And he went away to college at a young age and was one of those kid geniuses who was very much able to handle all of it. But yeah, he's a few years removed from the undergrad world. Yeah, he also, as an undergrad, he was one of the rare times ever UCI let an undergrad teach what he got to teach. yeah, he's he's a smart guy, but he's also really modest and humble and has a good way of looking at things. I mean, on top of everything else, you know, those people are geniuses and they tell you about it. But yeah, he's very humble because he worked his ass off to be where he's at. Nobody gave him anything in life, and I appreciate that his demeanor reflects that. But he's also somebody, he will help you out to the end of the earth if you need it. But that's why he's overcommitted, because he just basically helps too much. Anyway, let me get rid of this and back on track. Okay, so which of this is the smallest? I don't know, what would contribute to size? Perfect. Atomic radius to begin with, but there's a charge. So now we have to figure out where they are in the periodic table. So we have periodic table with sodium over here. That's number 11. Then we have Cl, fluorine, neon, argon I was going to put in, but we don't need. So tell me what's going to happen when they move. When this becomes F minus, moves up, did it just get bigger or smaller? It just got bigger. So F minus, protons 9, electrons 10. Neon is neutral, 10 and 10. Sodium also moves over here and becomes sodium plus. So it has 11 protons, 10 electrons. Do all three of these have the exact same electron cloud then? 1s2, 2s2, 2p6? But which one is going to be the smallest of those three? Why Na plus? Z effective. That positive charge is going to pull everything closer. Let me make sure. How can I eliminate chlorine? Chlorine's here. What's true of chlorine? Bigger shell. Biggest of all of them. Exactly. So it ends up biggest, second biggest, third biggest, smallest. So does that seem okay systematically? Perfect. So it's a little bit trickier when we toss ions in there, but hopefully it seems fair game. Okay. Which of the following does not affect vapor pressure above a liquid? This is one of those just brain teaser type questions more than anything. So what affects the vapor pressure? Let's define pressure first off. Pressure degree is force per area. Vapor is caused by evaporation. So I'm just going to toss those words up there. Evaporation, force per area. Okay. Will hydrogen bonding affect any of those? As hydrogen bonding, are molecules held together more tightly or less tightly? More tightly, exactly. More tightly held, harder to remove. That definitely will affect it. Will polarity, will dipole moments affect it? Sure. Will molecular mass, will heavier molecules be harder to remove than lighter molecules? So only one choice left. Why does surface area not matter? If you have twice as much area, don't you have twice as much vaporizing? You do, but because it's force per area, bigger area, more is going to evaporate, but divided by bigger area. So double the amount coming off, double the area. that forced area, the vapor pressure, stays the same. So vapor pressure depends on how easily the molecules can escape from the solution. Now, rate of vaporization, how many agree you want more surface area if you want to cool faster or evaporate sooner? So more surface area will definitely make it evaporate faster, but it's still going to be the same amount of vapor per area. Above the liquid, that's, I guess, what they have to decide, like where it exists, because vapor pressure, vapor can drift away from it. So they're just talking above the surface is whatever escapes from the surface divided by that surface. Because once it escapes, you agree these molecules can go every which way. So it's just the evaporated surface. So it's a little caveat they toss in there. It's more for the question whether to be anal about what they're saying. Okay. Why would a circuit be left open until the start of the titration? Okay. I apologize for not putting the picture of what's going on here, but basically you have two electrochemical cells connected by a salt bridge, connected by a wire, and then you're actually titrating one side with whatever you have, which means you're actually titrating in reactant. Okay, if you start titrating, is it going to react, or do you have to titrate and close a switch both? You have to do both. Okay, so why are you leaving it open? That seems kind of strange. So electrons don't flow. Exactly. That's the whole reason you want to leave that switch open until it's finally ready to go. And then we're set. So how do you answer that? Or actually I should say, what answer choice best describes that? D, perfect. So charging voltage, no, it's going to discharge. Prevent it from exchanging electrodes. What exactly does exchanging electrodes mean? I mean, somehow this moving there and this one moving there. They're not going to physically move. Yep, that's kind of a distractor. The main reason you don't is because if it's closed and you start titrating, you're already starting to lose voltage. So if you have any sort of reaction can occur, you're going to get some voltage drop. So you leave it open so that you don't run the current down. Okay. 37, the reduced voltage prior to reaching equivalence point can be attributed to which of the following? Okay, so what you have to see is that the voltage over the course of titration looks something like this. And then it shot up. And you're adding CR 207 2 minus. That's your oxidizing agent. And you were titrating, basically you have zinc, gosh, is it zinc chromium? My eyes have gotten so horrid at this point. Oh no, zinc graphite, so zinc lead, my apologies. So you're trying to react zinc lead, going to zinc 2 plus lead. And what is chromate doing? It's actually doing two things in here, it says. So the last one's unbalanced, but it's also reacting this way. So what's actually happening is when you're doing this, you're putting chromate in first, and it's reacting with the easiest one to react with, you get a voltage, but then is it reacting with another one? So the reduced voltage prior to reaching equivalence can be attributed to which of the following? Okay, so first off, is this possible? This is plus 6 oxidation state. This is oxidized. Is Pb2 plus oxidized or reduced compared to its lead form? So in other words, these are both oxidizing agents, they're both important electrons. So they can't really compete. They're not going to react with each other. They don't react with each other. So I'm going to get rid of that one. A redox reaction between this and this, kind of saying the same thing. Competing oxidation half reactions between this, possibly, and precipitation. Is it possible that lead, Pb2 plus, can actually precipitate? Would a 2 plus combine with a 2 minus? Yes. So what would that do? So let's say that did occur. If chromate, instead of actually reacting like we want it to do, what if chromate actually precipitated the lead out of solution? What would happen to this reaction if you got rid of the lead? No reaction. If you lose a reactant, limited reagent, it's gone. So actually what's happening is this chromate, weird as it may be, you're monitoring the voltage of the lead zinc cell. And as you titrate in chromate, it's precipitating, precipitating, precipitating until finally, right here, it is completely crashed out all of the lead. So now there's no more lead reactant. So that happens. But then if you keep on over titrating, it turns into this other reaction, which generates a higher voltage. Is that the passage from hell? This is just so overkill, but based on something from ages ago, but something that's valid, they like throwing weird stuff like this. So the titration is actually a precipitation at first. As you keep on adding it in, it keeps on taking away the lead, goes down, goes down, goes down, until finally when all lead's gone, voltage drops. And then it turns into the reactant in place of lead. So it takes over the reaction in place of lead 2 plus. This is a butt kicker. This is one of those that it beats people up. Do not lose sleep over this one. Okay. This, I think, is pretty important because this is an easy freestanding question. And is this the one equation I guarantee will be given on your test, the one that they will actually write? This is the one they will give you. Q equals MCAT. So if a 20-gram piece of metal at 75 degrees, heat capacity of 0.5, were added to 40 grams of water at 25 degrees, then what would the equilibrium temperature be, assuming no heat is lost to the environment? Whoa, this is going to be a tough one, I think. How many agree it's got to be somewhere between 75 and 25, which doesn't help me at all. So now I actually have to consider what's going into the relationship. So first off, what is the heat capacity of water? But it's a definition 1, perfect. So water absorbs more heat and there is more water. So do you agree it's probably going to be closer to 25 or 75? What's your instinct tell you? Going to be closer to 25, so it's going to be less than half. So I'm going to tell you straight out of the chute, I'm going to get rid of those two. I want to do intuition first. I still have to do math. There's no way I can get around math, but at least it helps me if I'm going to solve this to be a little bit more accurate. So heat cooling is going to equal heating up. So I have a 20-gram piece of metal with a heat capacity of 0.5 times T final minus, actually, let me make it 75. I'm going to make all my numbers positive. And I have the freedom to do that because there's a negative sign in the equation that I'm going to ignore. Equals 40 times 1 times T final minus 25. I'm hoping this math works out, but we'll see if it does. 10 times 75 minus TF equals 40 times TF minus 25. How many are okay with getting rid of that and making that 4? So the reason I did this, the reason I flipped this around is because it comes down to heat lost by the metal equals heat gained by water. Which means negative Q equals positive Q over here. I did T final minus 75 should have been what I did, but to get rid of that negative sign, I flipped those around. So ultimately, I subscribe to the I am so friggin' lazy that I want bigger number minus smaller number, bigger number minus smaller number. So therefore, I know everything's positive. And because negative signs didn't really come into play, I'm being utterly lazy. But that's where that came from. That's when I said there's a negative sign I got rid of by flipping that around. I was being lazy, not showing you my work, which I should have done. Okay. So I now have the following. I have 75 minus TF equals 4TF minus 100. Now it's a matter of just adding things across. So 175 adding 100 each side equals 5TF. TF equals 175 over 5, which is that 30 or not 30? Not 30. So therefore, I'm going to pick B and be happy with my lazy math. How many actually did the math and know that that is 35? Okay, so hopefully that seems okay. All right, onward to the next one. The vapor pressure due to ether above the ether ethanol mixture is the same as vapor pressure above a pure sample ether of the same temperature. Is that true or false? When you mix two things together, will you have the same vapor pressure, or do you now have an average vapor pressure of the two? You have some weighted average. So can I safely get rid of that? Is that the first one to go? Okay, so what next then? Is it affected by the addition of more ethanol? Sure, and the same reason that A is true, B must be true. If you change the percentages, you have a different weighted average. Okay, does it increase as the temperature of the solution increases? Is that true if you heat something up, true or false? No matter what it is, a mixture or pure compound, if you heat it up, more is going to evaporate. So you get more vapor coming off, more vapor when it's more temperature. And then finally, your pressure is higher if the system is open than it would be if we're closed. Misnomer. It's just if it's closed, it's trapped. If it's open, it can leave and it can re-evaporate. So that's false. Either way, vapor pressure is independent of open or closed system. It's just a matter of if we have a sealed system, we can trap the vapor and retain our fluid. Okay. Which one is for an excited state? Oh my gosh, would they really do something this mean and this evil? You bet. So you fill the sigma bonding first. You then form pi bonds. How many agree that this is the way OCHEM works? Carbon-carbon single bond, then a double bond, then a triple bond. How many would agree that when you fill it up, the single bond forms, then you the sigma first, then the sigma and pi, and sigma pi pi? So it does go that way. Pi star, sigma star. So if I want to write this electron configuration, sigma 2, check, 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 check. They all have it. Pi 4, check, check, check. Oops. Then pi star, whatever number it is. That's okay, that's okay, that's okay. But this is the one. Is that an excited state where it skipped the middle level? Organic molecule is anything that has carbons forming sigma and pi bonds. That's how we're just going to say organic, meaning carbon-based. Hence, I went with this. Carbons form to carbon, nitrogen, oxygen to other atoms. They form sigma and pi bonds. So hopefully that seems reasonable. What's wrong with 3? It's not full. So let me ask you this. Is this correct? Have I filled that correctly or no? What's wrong with this one then? That's a 2. I mean, they're filled up. What do I not have? I didn't complete this one before moving on to the next. So I skipped the spot here. So perfect, same thing here. I skipped the spot. I need to complete it with 4 before moving on to the next one. So hopefully seems okay. And so really, were they testing you on if you knew this by throwing it in a weird, unfamiliar fashion?
So
No doubt about it.
stable being excited?
Yeah, everything in the ground state.
Okay.
Yeah. Which following statement correctly describes the normal lung? It has a frequency of roughly 1.4 hertz. Ooh, teach me something, because I have no idea. How many breaths do we normally take per minute? Okay, so 12 to 20, 12-ish. Can I say 12 to 15 for a healthy person, a little bit more depending on who you are? So that means that's breaths per 60 seconds. So hertz is breath per time, or is it time per breath? A frequency, a hertz? So is that a pretty intense, I mean, would that be realistic? We've just said that somebody's taking about 85 breaths per minute. Is that gonna work out well for them? Yeah, so frequency is time of autumn, so that is a frequency. How's that looking? How many of you that's way too high? That's not gonna work out. It's gonna be anywhere from 0.2 to 0.25 hertz. Okay, airflow is associated with the lung airflow associated with the lung moves at a decreasing rate during a normal breath. I'm not really sure. Is that true? Sounds pretty consistent. Can I give that a question mark? Because I don't really know. But I do know, does it have to terminate? Does it start, pick up, then drop back to nothing? So part of it must be decreasing because it is eventually going to stop, but does it also start from rest and have to increase? So that's my question mark. Don't know what to do with that one for now. The airflow associated with the lung moves at an increasing rate during a normal breath. Ah, dang it. So which one is it? It increases, decreases, or does it increase, hit a max, then decrease back to 0? We exhale, and then during breathing in, we go from not breathing to breathing in to not breathing. So does it have to do this? Does it have to increase, then drop, increase, and drop? Meaning our breath, our lung is periodic. It follows a sine wave. So does that make sense? Does that seem reasonable? The number one's out. These hopefully seem okay. Tough question. Okay, last one of the day. So wow, this isn't, I mean, again, sorry we're way over time, but hopefully this is fine. So Raoult's law is a weighted average that says this is 75 and this is 150 if it were ideal. But if it's 40% B, then we're somewhere around here. And if I was looking at just B, it would be 40% of 75, which equals 30 torr, if ideal. So basically what we're saying is the partial pressure due to B is equal to the mole fraction of B times vapor pressure of pure B, which equals 0.4 times 75. That's where that number comes from. Okay, 30 is not an answer choice. But what this graph tells me is that's the ideal situation, but what's actually being observed is the actual vapor pressure a little higher or a little lower than ideal? A little bit higher than ideal. So therefore, should it be a little bit higher than 30? What's the best answer? Choice B, 30 plus a little bit. I don't know exactly how much, but I do know it's certainly not going to, this amount here, a little deviation is not going to knock 30 up to 70 or 80, and it does have to go up. Okay, for those of you who have not done these questions yet, I apologize if it spoils it, but I still think it's actually good exposure to see how these things work. Phase 3, based on the questions you just saw, let me skim through these just real quickly, because this was the last one, by the way. Realistic because it's based on an experiment or a device. Realistic because it's based on part of the body. Realistic because it messes with something that's common that you know, presented differently. Reasonable because it's based on experiment. Reasonable because it's based on experiment or devices. So the weird, this one's just a weird experiment. Weird experiment. Oh, shoot, now it's all stuck. So hopefully, I mean, do you notice that these questions are more, some of you know them, you don't, or you have to apply it, you have to recognize in context? Do these questions seem notably different than what you've been doing for homework? Can you see and feel the difference between phase 1 and 2 compared to phase 3? And more importantly, for people who've taken the MCAT before, would you agree phase 3 actually, the ones we just went over, do those feel more like what you actually saw in the MCAT? The homework questions beat the crap out of you, make you learn stuff. They emotionally tear at your soul. Do these questions tear at your soul a little bit less? There's some tricky ones, don't get me wrong. There's going to be some hard ones, but do you notice that they are more MCAT realistic, if you will? And the reason I want to ask you that is because if you're getting emotionally torn up on phase 1 and 2 over your scores, try your best to let it go. I know it's hard to do, but phase 1 and 2 are for exposure, not for realism. Phase 3 is where it gets more realistic. And again, just the feedback for anybody who's taking the MCAT, did the questions starting from 13 on seem a little more on par with what you remember the MCAT being like? So 2 yeses, private yes, so 3 yeses. Yeah, I'm hopeful that that's the thing you notice, that the realism kicks up and you realize it's how you apply it and it's how you stay focused without panicking. And so hopefully these if you do them, they go reasonably well. But So these last 4, 5, 6, 7, 8, 9, those questions were all from a phase 3. Shoot, I don't have. Sorry, I think my screen's moving forward. Trying to get to one last thing. Perfect. Sorry, it took forever to get there. The last thing, analyzing this pie graph. So again, sorry, went over, but yesterday, for anybody who came yesterday, we finished early. This is the offsetting thing. Like I said, moved a lot of questions from yesterday got moved to today. And a few people, well, actually, one person moved over. Anyway, that covers it. Have an absolutely wonderful night. I will see you tomorrow for thermokinetics. Normally, thermo is a lecture by itself. So the reality is it's probably going to be a little bit longer than normal. So I apologize way in advance. And then office hours again on Wednesday and Friday.
Thanks so much, Todd. When are the office hours? And I remember you saying that it's every day except 2 days. And I think I'm missing the day. So there's Friday, Sunday, Monday.
Yeah, so here's what I do in a given week. So Sunday, I have 5, well, I'm going to keep it as 5 to 6 plus, which I think we all know means 5 to 7 office hours. Monday is 4 to 5 plus office hours. And again, this is my time zone, so add 2. Tuesday is a 4 to 6 lecture. Wednesday is a 12 to 1 plus office hour. And then Friday is a 1 to 3 lecture. So that's what I do in a given week. Always the same link. Always whatever link you were here today, always the same thing.
Awesome. Okay.
And then,
Thanks so
and
much.
Jonathan has done an amazing thing. So have you gotten into the Discord page?
Yes. Jonathan is literally saying that.
Yeah. Yeah. Jonathan is amazing. And so the fact that he has the updates and
Yes.
just so that's, let's just say that blows the portal away. There's no need for the portal at all.
Yes, correct.
All righty. Okay. Well, thank you guys so much. And I guess I will see you lecture tomorrow and Wednesday office hours. Sorry, it helps when it's written in front. I like it. So, okay. And has Spencer mentioned when he's doing those yet, or is that still to be determined?
To be determined, I think.
Okay, because what I will end up doing is if he needs a slot of time that makes me move, I will move in a heartbeat to something else to make room for him to do his thing. Because I think that's one of the most important topics of all. So, all right. Yeah, I mean, Thursday or Saturday, if he can fit in those, that'd be great. But I hope there's like the same recording options will be available for those who can't make it. So that I don't know about. So anyway, someone will, hopefully. Okay. Well, I'm gonna kick out. Again, sorry this went so much over, but it bounced out yesterday's not going over. So